Welcome back. It has legitimately been 3 seconds since we ended part 2. This is part 3 of the Orgo Rapid Review, but I'm splitting it up this way because each level gets more and more difficult. It requires a more astute knowledge of organic chemistry, like I always say. So this is part 3. We're going to go over aldol, Claisen, carboxylic acid derivatives, enolates and anions, etc., etc., etc. So if you have any shred of dignity left, be prepared to lose it. Also, if you have not watched the entire organic chemistry playlist or the other 2 rapid reviews before this 3rd part, please go do that. It will help you tremendously, and it will be better for your mental health because we are going to hop straight into the high-yield difficult content. I'm recording, correct? Yeah. Perfect. All right. So let's hop into enolates, right? Enolates. So what is an enolate? Well, an enolate is an enol, and ate means negative ion, right? So what's an enol? We have an enamine. We know what an enamine is. We have an ene and we have an amine. So an enol is an ene and an ol, right? Is an ene and an ol. Perfect. So that's an enol. So an enolate would be that guy. That's an enolate, right? Shit. The moment you see that, shit. All right, so the classic enol reaction that you must know as an MCAT student is the Aldol condensation. Why is it called an aldol? Because you're taking an aldehyde and you turn it into an alcohol. All right, so let's take an aldehyde. What?
It never clicked until just
Aldol, aldehyde alcohol. Yeah. Aldehyde. Shout out to Professor Malitsky, man. All right. So you take this, and it is a base. Unlike other reactions where it was acid catalyzed, this is a base catalyzed reaction. We will talk about why it is base catalyzed in a moment. So OH and a little bit of H2O as your solvent as well. Okay. And the OH, of course, is catalytic. Catalytic means what? You put like a drop of it inside of your entire beaker, and the reaction just goes crazy, right? Hang the hydrogen, right? And the OH, the first step of the aldol condensation is the OH abstracts that hydrogen right there. That's going to make this, which is just what hiding in disguise. This is just an enolate. Which of these is major and which one's minor?
to the right is major.
On the right is major because the oxygen is holding the negative charge, which is better than carbon. Now, major contributors show you how the thing actually looks most of the time. Minor contributors tell you where the site of reaction actually is. So when this thing's going to react, it's going to react with that carbon, right? So let's take a look at how that looks. Well, let's take another one of these aldehydes, right? And let's take the guy that we just made, right? The aldol, or sorry, the enolate. Let's react them together, right? So this guy is going to cascade the electrons down and push this way because the aldehyde is a very electropositive position, that aldehyde carbon, right? And that's going to kick up these electrons. And that means we're going to make what? So these electrons got kicked up. This is now a single bond. We made a bond between this carbon and that carbon right there. So that's that carbon right there. And then we go up, this folded out, and we have a double bond right here. So it looks like this is what we made. And now the final step, this, right? And the solvent is water. So the water is going to get deprotonated by this, and that's going to form OH and OH minus. And since we reform the OH minus, that is a base catalyzed reaction. OH, OH. Makes sense, right? Okay, so that is the first product of the aldol. It is called a beta hydroxy aldehyde because this is the alpha and the beta carbon of the aldehyde. Correct? Remember, the aldehyde includes that carbon, so the alpha carbon is the next carbon, the beta carbon is the one after that. If you take that and you quench the reaction, right? So let's take a look at this. You have this, and you say step 1, NaOH. The product of step 1 is going to be this. If you quench the base with acid, who knows what the product's going to be? Does anyone remember? You will get an alpha beta unsaturated carbonyl,
I was gonna guess that.
or an alpha beta unsaturated aldehyde. Because of what? Because that is a secondary alcohol in the presence of acid. It's going to dehydrate, right? So the mechanism is the same as an alcohol dehydration. So if we take this, the product of part 1, the product of step 1, and we put it in a reaction vessel with acidified water, right? Hydronium. That's going to make this. This guy's going to leave. And you get elimination of this hydrogen right here. And that's going to make this. And the reason you preferentially 99% of the time eliminate this hydrogen is because that makes a conjugated system with the aldehyde. So you get very, 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 very little of the Hofmann product. Huh?
Wait, so that's an aldol condensation?
Aldol condensation. That is part of the aldol condensation. This whole thing is referred to as the aldol condensation. But the second step is called quenching the aldol. What time is it?
9.
Okay.
I don't know why.
You guys okay to be here till 10?
Yeah.
All right.
We ball.
Let's do it.
Fuck it, we ball. I told you this is going to take a while. For all the people watching back home who have the liberty of watching this in pieces, we have been here since 7:15 and it is now 9 o'clock. And I have an exam to study for. That's how much I love you guys. Y'all better send your patients to me in the future. I'm kidding. You can take care of them yourselves, I'm sure. Okay, so that was the aldol. The Claisen doesn't really come up as much, but every now and again, it does, I guess. And one more thing, the Michael comes up every now and again. So let's talk about the Michael and the Claisen. So the Michael is just doing the aldol on an aldol product, right? So let's say that you had an aldol product like this, and then you took that, and the aldol kind of continued, right? So you deprotonated this, and you made this. So the Michael addition is when you do this. So let me draw this beside this guy. Hold on. Let me draw this way. I'm messing myself up now. And then you have the aldol product, which is the alpha beta unsaturated, right? The Michael addition says that you take these electrons. I still drew it the wrong way. Start over.
Get it together.
It's hard, okay? It's difficult. All right, so this is our starting thing. And from this, we made what? We made this, right? If this reaction continues, so we deprotonate this and make another enolate, that enolate can actually attack what? This. And this will flip up and flip that way. And that's going to create what? Well, this is hard to draw, right? So I'm going to number these. 1, 2, 3, 4, 5. So 1 connects to 2, connects to 3. 3 has a methyl group on it and connects to 4 and to 5. 5 has an O minus. 1 has a double bond. And then what else? 4 and 5 are connected through a double bond. And that's it. Right? Okay. And then, when you quench that, you get what? Oops.
Quenching is just protonating, right?
Yep. You quench it with an acid. And then this, that's an enol, and you quench in acid, so it's going to undergo a keto-enol tautomerism. So it's going to tautomerize into that.
How do we name that thing?
Very pretty, right? This.
It won't be that big.
3-methyl butanediol. 3-methyl butanediol. I think. Maybe. I don't fucking know. Maybe I'm wrong. Sue me.
How do you know this quenching base of acid?
So when you have a base, when you have a reaction filled with base, you pour acid inside of it and it stops the reaction. That's called quenching. Also, did I add an extra carbon to, hold on. No, right? Yeah, and then oh, so that means I fucked up in my notes. Not here. Okay. That's fine. I don't give a shit about that. It's not in my notes, but we'll go over it real quick. The Claisen condensation. No.
That's exactly how I feel about it. It's like a combination.
The Robinson annulation is like an aldol. It's like an intramolecular aldol. No, it's intramolecular Michael followed by like an aldol, and then like it's so weird. It's
very
it's so dumb.
Yeah, so it's Michael, then Aldol.
Okay, so this guy, right? Is that correct? No, it's not. Because this will just substitute and make carboxylic acid and deprotonate. So we have to use NaOET. And that's going to deprotonate without substituting. And that's going to give us this. And we can add this onto this. That's going to give us what? This is so hard. I hate this stuff. Carbon attaches to O minus. And then O minus comes down and kicks off, and that gives us there you go. Someone who's better at orgo than I am, quote me on that. Count my carbons, check the mechanism, make sure I'm not fucking up. end product should have 4 carbons, correct? 1, 2, 3, 4. OET. OET gets kicked off, and then I think that's good, right? And no double bonds because we kicked off the OET. Yeah. I want to make sure of that one. It's been a minute since I did Claisen condensation. It's correct. Always doubt yourself. Always. People say, oh, never doubt yourself. You never doubt. Shut the fuck up.
Especially on the test between 2 answer choices.
Okay, wait, that's different. Hold on. Wait.
That's what
Always doubt yourself to a healty degree.
before the test.
Yes, before the test. Laura's going to be sitting down like, I don't know what glucose is. I don't know anymore. Is it a sugar or a lipid? Oh, man. Carboxylic acids, how do we make them? How do we make carboxylic acids? We oxidize alcohols, right? Right. Also, fun fact, what is vinegar? Vinegar is acetic acid, otherwise known as ethanoic acid, right? So acetic acid is vinegar, and that's 2 carbons, right? Even though it doesn't look like it, it's 2 carbons. Yeah, I always thought this was 3 when I was like learning orgo. It's 2 carbons. 1, 2. So what alcohol does it come from? Ethanol. The alcohol that people drink. Not me, but people do, right? So when ancient societies were making mead, what is mead? No, mead. Mead is wine. Mead is a very ancient form of wine made with honey, right? Or with grapes. So grapes is wine and then honey is mead, right? So when ancient societies were making mead, or the Greeks and the Romans were making wine, right? They would take the sugars inside of the grapes or the honey, and what would happen is that bacteria, which aren't that great at processing sugars, would turn the sugars into alcohol. Or yeasts would turn the sugar into alcohol, right? Now, once it became alcohol, they would drink it and they would get drunk, right? They would get tipsy, they'd get drunk, they'd have it all at their celebrations, blah, blah, whatever. And the alcohol would be left out in these barrels. And now, when we barrel age alcohol, it's airtight, and nothing can get in, nothing can get out, very well, a temperature-controlled thing, blah, 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 whatever. I don't exactly know the details of it, but it interests me because it's science. All of it is science, right? But if you don't control the aging of alcohol, it's going to oxidize in air, which is why airtight barrels are used to age alcohol. So when the oxidation occurs, the first step of the oxidation, right, is the alcohol into a aldehyde, right? So then you get acetaldehyde. Now this happens inside your body, right? And there is an enzyme called alcohol dehydrogenase, which uses NAD+ to turn into NADH and H+, and this acetaldehyde accumulates in your body, and that's what gives you a hangover, right? So the acetaldehyde is what gives you a hangover. But so now you have 2 separate layers. In that barrel that you're making, you have 2 separate layers, and one of them is alcohol and one of them is acetaldehyde. If you let it ferment even longer, the acetaldehyde will eventually turn into acetic acid, vinegar, right? And another enzyme in your body can do this, and this is called acetaldehyde dehydrogenase. And this is actually how you urinate out alcohol when you're done drinking. It takes another NAD+, turns into NADH, and it makes vinegar, and then you piss out the vinegar. Very, very dilute, right? So your piss doesn't smell like vinegar unless you've drank an entire fucking classroom's worth of alcohol, right? But now you have 3 layers, and one of the layers is vinegar. And if you've ever seen vinegar being made, there's this thing called mother of vinegar, and it's this population of bacteria that are constantly oxidizing the alcohol and the acetaldehyde. So those bacteria are making vinegar. And what happened is that the Greeks or the Romans or whatever ancient civilization would come and they dip their glass inside of the alcohol and they drink it and they're like, oh, it's sour. But not a bad sour, a good sour. And that is how we discovered vinegar for cooking. So when they say balsamic vinegar, white vinegar, red vinegar, champagne vinegar, it just depends on what alcohol you started with to oxidize to make that vinegar. So red vinegar is from red wine, white vinegar is from white wine, sherry vinegar is from sherry, right? Champagne vinegar is from champagne. Huh? Balsamic wine.
Oh, that's wine?
Yeah. All right, so we oxidize alcohols in order to make carboxylic acids. And then with carboxylic acids, we can do a fuck ton of chemistry. A absolute heap of chemistry. Huh? Yeah, carboxylic acid derivatives, right? So let's look at the list of carboxylic acid derivatives one more time. So we have the acid chloride, and then, guys, what's next? Come on, you know the list. Anhydride, yep, and then the thioester, and then the ester, and then in this realm would be the ketone and the aldehyde in terms of electrophilicity, and then the amide, and then all the way at the bottom the carboxylate. How do you get any of these to do their thing? I'm going to show you one. You can elucidate the rest. This one. Carb acid. ROH, ROH2 plus. Assisted leaving. And the schematic is that long, if not longer, for the rest of them. For this, you will use ammonia and ammonium. For this, you will use protonated HSR and HSR. For this, you will use 2 carboxylic acids. And for this one, you will use SOCl2 and pyridine. Don't worry about the SOCl2 one. It's different than the rest of them. What's the point of listing them like this? This is in order of electrophilicity, meaning this is in order of how much the carbon position here wants to be attacked. Carbon position where? Carbon position here, and here, and here, and here, and here, and here. And that's dependent on what? It's dependent on the favorability of this group leaving. So what I'm saying is as you go down the list, the group wants to leave less. And as you go up the list, the group wants to leave more. And that's all based on conjugate acid pKa. So what's the leaving group here? The leaving group is Cl minus. What's the conjugate acid? HCl. What's the pKa of HCl? Negative 5. What's the conjugate here? It's a carboxylate, which the conjugate is a carboxylic acid. And the pKa is 3 to 4. What's the conjugate here? It's SR minus, or RS minus, sorry. Why did I say RS minus? Because the negative is on the S, right? Conjugate is RSH, pKa 8, RO minus, ROH, which is alcohol, 15 to 17. NH2 minus, conjugate is NH3, pKa is 38. And that doesn't have a leaving group. You're not going to kick off. This. That's not happening. You see, the acid becomes more and more stable, which means the base becomes more and more unstable, which means going up, the base becomes more stable, which means that the position becomes more electrophilic. And that means that this bond and this bond and this bond and this bond and this bond, when cut, the energy released from cutting that bond increases as you move up the list. Which is why when you cut ATP, which is a phosphor anhydride, you release a lot of energy, right? But cutting a protein requires energy. This is why you need to watch the videos before coming to the rapid review, because that was a whole lot of bullshit if you did not watch the lecture before. There's like, I think we went over this for like an hour and a half, like in the actual lecture. We went through this a while. All good in the hood? Carb acid derivatives done. We're not going over spectroscopy, and we're not going to do lab techniques until the end. All the way at the end of my notes, there's a picture of my cat.
Aw, thank you for the serotonin boost.
There is a small picture of my cat. And now, cramp gone. And now, the pKa table. Which, do I recommend you dedicate it to memory? Yes. Will you? No. But we'll do it anyways to take a look at the chemistry that's involved in certain specific parts of the pKa table. We start with HBr, HI, HCl, H3O+. Oh, sorry. Wow, I'm rusty. Medical school is doing a dance on my MCAT knowledge. All right. Yeah, I think I'm holding my own pretty well. All right, HF, and then what was it? It was, so that was HF and then COOH, so our carboxylic acids, right? After our carboxylic acids was our bicarb, our carbonic acid. Then we have RSH, then NH4, and then after NH4 we have HCN. After HCN we have water, then alcohol, then a acetylide, then NH3, then ethylene, and then ethane. Let me draw it like this. Because it like kind of helps to visualize what exactly is getting plucked off. Oh man, welcome back. Where were you? Oh, good. When's the test?
Tomorrow and Thursday.
Wonderful. Good luck. I will see you here after the exam. So that you guys can cry to me about how difficult it was. Did you cut your hair?
Yes.
Looks good. Wonderful. Very good. We're almost done. It'll be another like 10, 15 minutes or so. All right. So these are the acids, and these are their pKa's. negative 9, negative 7, negative 5, 0, 3, 3 to 4, no, sorry, 4 to 5, 6.2, 8, 9.4, 10, 15.7, 16 to 18, depending on the size of the alcohol, 25, 38, 40, 50. Now, to someone who walks into the room and sees that, this makes absolutely no sense. So let's talk about what we mean with these numbers. Well, first off, we have to know what acid theory we're talking about. It's obviously Bronsted. All of these have an H attached to them, right? All of them have an H attached, right? So the next question is, what are these numbers? They are called what? They're called pKa's. Well, what is pKa?
Log of Ka.
The negative log of Ka. What's Ka? Ka is the dissociation constant of a specific acid in its reaction with water. So let's take a look at that. If we have an acid HA and we put it in water, it's going to dissociate according to the reaction H3O plus and A minus. Oh my god, I haven't checked my microphone in so long. If my audio had cut out, I would have killed myself. Not actually.
Like and subscribe.
Like and subscribe, guys. If you need help, please call the suicide hotline.
Be here next episode. We will be.
All right, so H3O plus A minus, correct? Now, if we're writing a K expression, it's concentration of products over concentration of reactants, correct? So the Ka is going to be the H3O plus and the A minus, which is just the concentration of dissociated products, divided by the concentration of the HA, the non-dissociated products. Why does the H3O not go in? The H3O is there. Where is it? Where did I say it was? It's hiding in the brackets. It's hiding in the brackets. Because the bracket means concentration. Concentration in what? In water. Because the whole thing's happening in water. So these concentrations are all in water. Because those concentrations are in molarity, which is moles over liter. Liter of what? Liter of water, right? That is a Ka. So that means that the negative log Ka is negative log of H3O plus A minus over HA. That is the pKa. You guys want to get fancy? Technically, because you can distribute a log through a multiplicative product, through a multiplicative formula, right? So now this is easy to see why, right? Increases in the dissociation are going to do what to the pKa? Increases in the dissociation are going to increase this and this. And if this goes up, the pKa is going to, it looks like it's going to go up, but remember, it's going to go down. Increases in these are going to bring the pKa down. So a lower pKa means more dissociation, which means a stronger acid. And a stronger acid has a weaker or more stable base, otherwise known as a conjugate base. So the most stable conjugate base we have is I minus, then Br minus, then Cl minus, then H2O, then F minus, then a carboxylate, hello old friend, then bicarb, then RS minus. Someone's running away. Got scared. NH3, Cn minus, OH minus. Also, oh no, not also OH minus, OR minus, or RO minus, right? And then this is the acetylide anion. Amide, potassium amide, sodium amide, right? Then that, and then that. So now I can show you what I meant back in part 1 when I talked about SN1, SN2, blah, 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 whatever, the strong bases, the moderate bases, right? The moderate bases are here. The strong bases start here, and these are the negligible bases. Because the water, the hydronium and the water are the cutoffs for everything. So these are strong acids, moderate acids, weak acids. Negligible acids. Negligible bases, moderate bases, strong bases. Does that make sense? However, don't take a photo of that. Because I find that when I put the conjugate bases here, people start to get mixed up. They read in the opposite direction. That was simply for your knowledge and enrichment. If you're going to take a photo, I want you to take a photo of that. Wait, hold on. That. Yes?
To sum up the pKa, so pKa means more dissociation, which means a strong acid.
pKa is the negative log of the dissociation constant. Since it is negative, it is inversely correlated with dissociation. Stronger acids dissociate more, and since pKa is negatively associated with dissociation, it will go down. You can always find it on the YouTube channel. Have you guys had enough of Orgo? One final thing. One final thing. The leaving groups for the carboxylic acid derivatives, where are they? One of them's right here. One of them's right here. Oh, sorry. One of them's right here. The anhydride, yeah, is right here. One of them is right here. One of them's right here. Yeah.
Is HCl not leasing for?
Not for the carboxylic acid derivatives. So, and the thing is, it's not the acid that gets kicked off, it's the conjugate base. So what's the conjugate base that gets kicked off? It's Cl minus this, and this. So this gets kicked off of an amide. This gets kicked off of a this gets kicked off of an ester. This gets kicked off of a thioester. This gets kicked off of an anhydride, and this gets kicked off of an acid chloride. Like I said, the stability of the conjugate bases goes up the pKa table because these are the stronger acids. So you can see how the acid chloride has the most favorable leaving group, then the anhydride, then the thioester, then the ester, then the amide. And you can prove that using math. You can prove that using the pKa. I can write out a proof for you. Right? All right. Trying to think if there's anything left that I want to talk about. Oh, the difference between these S character. How much S character do you have? And I hate the S character term, but I know it's what they use at Brooklyn College, right? So the S character, 50% S character, 33% S character, 25% S character, right? 25, 33, 50, right? And what I like more is that this has 2 p orbitals, which are electronegative. This has 1, which is electronegative, and this has none, which are electronegative. So the ability for the conjugate base to accommodate the electrons is higher when there are more p orbitals, because you want more electronegative things. One last thing, and then we're gone. The Ka of acetic acid is 1.8 times 10 to the negative fifth. You guys know the answer I'm going to ask you. Or the question I'm going to ask you. I want you to calculate the pKa. The log of 2 is 0.3. The log of 6 is 0.8. And the log of 8 is 0.9. If you have log AB, you can rewrite it as log A plus log B. And that's all you need to know. So to calculate the pKa, we take negative log of 1.8 times 10 to the negative fifth, right? This can get rewritten as negative log of 1.8 plus negative log of 10 to the negative fifth. Well, the log of 10 to the negative fifth is negative 5. The negative log of 10 to the negative fifth is 5. Right? The negatives cancel out. What's the negative log of 1.8? Well, the log of 2 is 0.3. So it's going to be slightly less than 0.3. Let's say it's 0.25. Negative 0.25. Plus 5 is 4.75. You go on your iPad and look up the pKa of acetic acid.
4.74.
Are we that far off? No, we're not.
There's no calculator on that.
Yes?
Real quick, can you show us that hybridization trick thing? The hybridization, like
Which one?
one is with two.
Right. Okay, I know what you're talking about. My little trick, the little counting thing.
Yeah.
Right. Okay, so if someone asked you, what's the hybridization of the carbon in the central carbon in this compound, right? One thing you can do is that whenever you're working in organic chemistry, they probably won't ask you about d orbital hybridization because you need what? Transition metals to do that. Or a phosphorus or a silicon or blah, blah, whatever. Right? So this carbon right here, what I do is I throw down my letters. I go S, P, P, P. What does that stand for? It stands for the sublevels within each of those orbitals. The S has one sublevel, the P has 3 sublevels. Now, the carbon has how many electron domains? 1, 2, 3. If it has 3 electron domains, I go 1, 2, 3. How many S's did I cross off? 1. How many P's did I cross off? 2. And the best part is you see this P that was left alone? That is the free P orbital in the middle of the molecule. Next, let's do acetylide. This carbon right here, right? S, P, P, P. 1, 2 domains. So it's just sp hybridization. Those 2 p orbitals are the one that are running perpendicular in both directions. Both of them are attaching to that carbon over there. Let's do a carbocation. One, two, three. 1, 2, 3. sp2 with a p orbital running in the middle. Okay? Yeah?
What about the lone pairs? Remember you said you count the lone pairs also, right?
But, however, now what is that? Now it's sp2. Why? Because it is next to that and it can resonate. And if it, remember what we said way in the beginning, if it does resonate, right, it has to be sp2. And this does, right? If it does resonate, it has to be sp2. You can't cook a soup without water. You can't resonate without being at least sp2. All right? Thank you guys so much for attending. I hope you had a great time and I hope you learned a lot. And next time we will circle back on more biology rapid review. And after that we'll do biochem and then gen chem and then bio and then biochem and then gen chem and then bio and biochem and then gen chem. And we'll keep going until you guys are going to take your test. The last day of the program is to be determined. Thank you guys so much for watching.